posted to our Ascension Lakes YouTube channel, so you can find it and share it with others if you'd like. And we just ask that you keep your microphones off and your cameras off during the presentation today to make it run as smoothly as it can. So at this point, I'm going to turn it over to Jonathan. You can start sharing your own screen.
Thank you for inviting us, Paul. Steve and I have had so much fun talking about weather and climate science for a number of years on the public radio station. And so it's great to get out and talk to other groups in some detail. What we're going to do today is I'm going to provide maybe a broad scale overview of some of the science that underlies what goes on in the wintertime. And then Steve's going to talk about this crazy winter we just had. And I think that's going to be a nice combination of how we're going to go. Steve, why don't you introduce yourself too?
Yeah, my name is Steve Ackerman. I'm the other weather guy. And so if you ever have questions, you can find our emails and send them to us. And when we're on Larry's show every last Monday of the month, we'll try and address them.
All right.
And we look forward to hearing your questions at the end of this.
Very much so. We've made sure that we're going to have time for that. So I guess I'll just get started. Wait a minute now. Here we go. I'm going to go back and start this movie again. In the middle latitudes of Earth, there is a constant parade of weather systems. And this is a satellite mosaic from October of 2016. The only reason I have that is because it just happened to be handy. And if you concentrate on the middle latitudes, that is everywhere above the tropics, either in the northern hemisphere or the southern hemisphere, you just see an endless number of swirlies going around this movie that's about a 10-day animation. And they are constantly percolating in the middle latitudes. And these weather systems, these swirlies, are in fact what we call our cyclones and anticyclones that give us our day-to-day weather and the transitions between the weather from one day to the next. And what I want to say today is some of the basic characteristics of what drives these things. And you might look at this movie and say to yourself, it looks like it's chaotic. It's almost like I poured cream in my coffee cup. But all of these disturbances are obeying physical laws. And those physical laws are fairly well understood. And we can use the understanding of those physical laws to actually make some sense about how these storms behave and thereby make reasonable predictions. And I say, reasonable in the sense that I think if you can paint the complexion of the coming day at 5 days or at 7 days or at 10 days, which now undeniably numerical weather forecasting allows us to do with great regularity, that's a revolution that has gone on in the last 50 years or so. Honestly, not more than 80 years. That is an absolute invisible revolution, and it's changed everything about the way I think we live our lives. So we're going to talk a little bit about what goes on with these storms. The Earth is tilted at about 23.5 degrees to the so-called plane of the ecliptic, and that is the plane that contains every celestial body in the solar system, including the sun. And so what I'm showing you here is the fact that, and this is the winter solstice picture that I'm showing you, the Earth is showered with radiation from the sun. And because the Earth is spherical and tilted on its axis, this results in an uneven absorption of that solar radiation across the globe. And we all know this from our day-to-day experience. I mean, we're seeing a later sunset right now. We're seeing gradual warming. And these are all consequences of the fact that this tilt and the orientation of the Earth, I should say, the orientation of the Earth to the sun in its orbit around the sun is mid and making it a little bit less intense cold. And eventually it'll make it the most intense warmth we can have. And that'll be late June. So this distribution of radiation is a major factor in driving the climate and the weather around the globe. The high latitudes in this picture, see if you can see my pointer. At the very high latitudes, this solar energy is coming in at a very low sun angle. And so the intensity is low. And if you're at 23.5 degrees or so south in the southern hemisphere, you're getting the sun directly overhead at noontime on the same day that we have the lowest sun angle in the sky. So big differences in the amount of radiation, and they change during the year. The consequence, though, of that broad picture is that certain locations on Earth receive more radiative energy from the sun of a year than other places do. And that curve is the red line. This is the incoming solar radiation from all the latitudes from the North Pole to South Pole. And the integrated over year peaks right there at the equator. And then the whole Earth is warmer than 0 degrees Kelvin, so it's emitting its own radiation, not quite solar radiation. It's not warm enough to do that over its entire surface. And that amount of emission is in the dashed blue line. And it also peaks in the tropical latitudes, but the difference between tropics and high latitudes is not as great in the infrared emission. And so it sets up a situation in which the tropical latitudes have a net plus of incoming radiation against the outgoing over the course of a year, and the high latitudes in both hemispheres experiences a deficit of that radiation going out than coming in over the course of a year. Now, if that were unmitigated, the tropics would get systematically warmer every single year, and the mid latitudes and high latitudes would get colder. But that does not happen. And so radiation can't be the only game in town. It's the primary game in town, and it pushes other ones around, but it's not the only game in town. In fact, the only way to make sense of the observation that this does not happen is that this surplus energy in the low latitudes has to be transferred by the atmosphere and the ocean to higher latitudes. And that transfer is accomplished by three major physical mechanisms. One of them is ocean currents on a water planet like ours. We have in the western boundary currents of all of the major ocean basins, warm water is pumped poleward, and in the eastern currents along the coast of Africa or along the coast of the United States on the west coast, cold currents of water are pumping cold water towards the equator to get warmed up by the surplus. Another mechanism is latent heat. You can evaporate a lot of water in the tropics, which are mostly ocean, by virtue of this surplus of energy. And that water vapor, which is visible than oxygen or nitrogen or any of the other ones, can be exported to high latitude where it can change phase. And when it changes phase into clouds, either liquid or ice, it releases the exact same amount of energy that was required to evaporate it in the first place, but it's released in a different location. So this is a stealthy way to from the surplus regions in the tropics. But the one that I'm most interested in as a mechanism is the parade of cyclones that we started out with on the satellite movie. At middle latitudes, these storms come in sequence. Regions of low pressure, which are characteristically associated with clouds for reasons we'll describe in a minute, are usually followed by or anticipated by a region of high pressure, which has different characteristics. In the northern hemisphere, the circulation around regions of low pressure is counterclockwise, as I'm showing you here in this simple diagram. And it's a north, south, east, west diagram that you can tell. And then the circulation around the regions of high pressure that are adjacent to these lows is clockwise in the northern hemisphere. And so you'll notice that in between the two, there's cooperative interference. There's poleward here, straight equatorward here, and straight poleward here. In fact, those parade of cyclones that I started the presentation with is actually actively pumping cold air equatorward so that it might be warmed up by the surplus of radiant energy, and it's pumping warm air poleward where it might deposit some of the excess energy that it received at low latitudes. And so these storms are doing a really big job in alleviating that surplus deficit. In fact, mid-latitude cyclones, even not counting a latent heat trick, which they also can incorporate, just this sensible heating of moving warm and cold air around is 40% of the total surplus deficit alleviation. So they win. They do more than anything else to make that happen. Now, if we look individually at the cyclones or anticyclones, they're interesting all by themselves. Cyclones are regions of low pressure at their core. These storms are right at the surface, and so the surface is a frictional surface on Earth. And so there's going to be a little bit of convergence of air into the regions of low pressure, as I'm showing you on this picture. And that forces, near the center of the cyclone, that forces the air to rise in the green arrow. And rising air will expand into its lower pressure environment. The pressure gets lower the higher up you go. As it expands, it cools, and its relative humidity increases. So if there's any water vapor in it, and it's really hard to find an air parcel on Earth that doesn't have some, you're going to have an increase in relative humidity, which leads to clouds and precipitation forming. This is why regions of low pressure are characteristically associated with clouds and precipitation. And the rising air also evacuates mass from the column right above the region where the pressure is already lowest. So if you're taking this air out by virtue of that green arrow and depositing it in adjacent air columns, you're making that column less massive. So the pressure keeps going down for a period of time during the life cycle. Characteristically, these storms get more intense for a period of time, and then they begin to decay, and there's reasons for that, but that won't be part of our conversation today. But while they're continuing to intensify, this process of producing clouds and precipitation also intensifies. Near surface air diverges away from regions of high pressure. And so that's what the picture looks like here. At the center of the high pressure region has the highest pressure in the whole environment. And that air is, because of friction again, is forced to go across the isobars, the lines that are drawn there in red, constant pressure lines. And there's a little bit of divergence at the surface. This is accompanied by sinking air over that column. And if the air is forced to sink, it warms up because it's being compressed as it moves to higher pressure, and its relative humidity decreases. And clear skies often are the characteristic of the anticyclones, the spaces between cyclones. And in the wintertime, that makes it pretty cold because you have a long night and you've got snow on the ground, and clear skies makes it easier to radiate energy away. In the summertime, it also makes it a little bit cooler than it might otherwise be, but you have the at night anyway, but you have the compensating high sun angle in the summertime, in the daytime, that'll make it really warm. So it's not quite as obvious that that'll be the case in the summertime. And the sinking air, again, also forces mass into the column of air that's right above the anticyclone. So for a period of its life cycle, it keeps getting more and more intense. And so this process of subsidence, that is sinking of the air and divergence at the ground, is exacerbated, and you can have a prolonged period of clear skies. And another thing that characterizes both of the hemispheres, I'm drawing you a northern hemisphere picture here, is that, of course, by virtue of the tilt of the Earth's axis, it's always colder at high latitude in any hemisphere than it is at lower latitudes. And so you have a north-south temperature gradient in the northern hemisphere, colder to the north, warmer to the south. And these red dashed lines are lines of constant temperature. And so you get colder as you move to the north. And that temperature gradient, that difference in temperature over that horizontal distance, supports what's known as a vertical wind shear. The wind speeds get stronger and stronger and stronger as you go up through this column of temperature contrast. And that's a characteristic of the way that the fluid atmosphere behaves. So what we end up having is, at the tropopause level, the top of our troposphere, in which most of the weather occurs, we're going to have highest wind speeds of the entire column. And sometimes there are local maxima in those high wind speeds that are known as jets or jet streaks. And those jet streaks have characteristic distributions of vertical motion associated with them. There's rising in the so-called left exit region of the jet, which is, here's the exit region. Air is leaving the jet on this side. And there's rising in the right entrance region. This is where the air enters the jet over here. And then there's going to be companion regions of sinking air that look something like that. And this is important because this will be these will be preferred regions for cyclones to develop, at the left exit region of the jet or at the right entrance region of the jet. And in many instances, you might have a picture like this where the streamlines of the flow 3 to 5 miles above the surface look like this. The atmosphere has tons of waves in it, and these waves are manifest in that satellite picture. You could see them. That's what makes them look like swirlies. So these waves also have a tendency to produce distributions of vertical motion that aid in the development of cyclones. Here is what we call a trough. I'm drawing the cursor right through it. I hope you can see that. And downstream of that, to the east, is a region of ascending air. And upstream of the trough, in this region right here I'm circling, is a region of descent. If you put a jet in that region on the west side of the upper trough, then you're going to have not only the ascent forced by the change in the direction of the flow, which is indicated by the red streamlines, but also the left exit region of the jet. And so this is where your cyclone is going to develop. And that's characteristically the case. And there may be an anticyclone developing right over here. And that's how they come in sequence, related to these waves in the upper part of the troposphere. And when you get a decent cyclone development, probably all heard about warm and cold fronts, even from just the broadcast news. The circulation around the storm is indicated here as counterclockwise, which is characteristic for the northern hemisphere. And you get a tendency for all the air south of the warm front and east of the cold front to be uniformly warm. And it's quite warm in decent, well-developed storms. And then it's relatively cold everywhere else, as you can see. And in the wintertime, that warm air can be really warm, and it can be pushed poleward almost all the way to the North Pole in extreme cases. And then the cold, of course, as you might guess, if it's drawing on air from central Canada, it can be really cold in January. And so that's how we can have our big swings in temperature that sometimes characterize our winter in here in the middle part of the United States. So that's the broad picture of what winter storms, how they might form and how they might be related to what you see on the satellite picture. And we all have our own stories and a fascination about the precipitation that comes with them. One of the things that's caught my eye over the last several years, generated by, this past winter was really boring here for me. I like snow and I like a kind of a cold winter. It was not unsimilar to 2011-12. And I started to look at, I got frustrated by the fact that the winter was so boring locally. And I thought, I got to get out of this parochialism and don't drive myself crazy because I'm having such a boring winter. So I thought, how can I do that? Maybe I can measure the intensity of the winter by proxy. So if it's intense somewhere else, I can get excited, but also maybe I can get a sense of where is the winter kind of intense and what's going on there. So I started looking at the areal extent of air that is colder than -5 degrees Celsius, which is 23 Fahrenheit, at the pressure level 850 millibars, which is about 1 mile above sea level. And so here's just one instantaneous example from a long 76-year time series now that I have access to that shows wintertime, one day in the wintertime, of the areal extent of the -5 air at 850 millibars. So you can see that this is a pretty big blob of relatively cold air that covers all of the northern latitudes of the northern hemisphere and ekes its way into the northeast United States on this day, a little bit south of the Aleutian Islands and some other places it's covering Western Europe. The light blue shading is an area that's easy enough to calculate with gridded data. And the outside line, the blue line, is the actual isotherm itself. So I started to calculate this just to see what it looked like every day. And here is what this past winter looked like. I got to explain this diagram. I've got a 76-year time series of exactly these areal extents every day. And the maximum that it's ever been on December 1st is right at this point. The minimum it's ever been on December 1st is off the graph. And that's what those thin blue lines indicate, the range over the whole 76 years of how big or small has that areal extent of cold air been. Then this solid blue line in the middle of the gray shading is the actual average for every calendar day from December 1 to February 28th over that 76-year time series. The gray shading represents +1 standard deviation above and -1 standard deviation below that average. And then finally, the red line is the daily time series of the actual areal extent of the -5 air at 850 millibars from this past winter. And I think, if you're looking at the distance between the red line and the average for the calendar day, there are only a few times all season where the actual value for a day was above the average. A couple of days in early December, one in mid-December, a couple of days in January, and then never again. And this particular year is fairly characteristic of what's been going on in the last 20, and I'll save that for just the next moment. But what I can also do by tracing this has gotten to be a really fun little research project, is I can just figure out what's the average for the entire 90 days from December 1 to February 28th. I just add up the daily value for each day and then divide by 90. And this is what that time series looks like all the way back to 1948-49. Every one of these black dots represents the seasonal average, December 1 to February 28th, for the given season. And so I'm going from 48, 49 to 23, 24. And the red line is the trend line, which is at 99.9% significance. We used to be around 70 million square kilometers in the early 1950s for this cold air over the whole hemisphere for the season. This last year, we were just below 65 million square kilometers. And you might say, that's not such a big deal. But 5 over 70 is like 7.3%. So we've had a systematic, the red line being at that significance level. This is a systematic decrease of 7.3% since 1948-49. We are warming up during the winter in a systematic way that's observable and away from the ground, uncontaminated by urbanization or whatever else might be something a skeptic could throw at you about what does the trend mean. And then the last thing I've got to show you is this. This is the integrated departure from average for the whole season for all the years in the time series. And I'm ranking them by the warmest. Number 1 is the warmest year ever. And look at number 3 was 2023-24. We just barely got nudged out of second place all time on the last day, February 28th, by something the size of the Louisiana Purchase, something that minuscule pushed us out of second place. But this is an astounding track record. If you look at the top 10 stopping right here, there's only one of them that occurred before 2003. So since 2003, only 21 seasons, 9 of them have been in the top warmest ones ever. It's systematic that the entire record is being affected by the gradual global warming, and you can see it at 850 millibars in this cold pool analysis. So the winter is changing, and I gave you some indication of what the broad scale characteristics of winter are. Here's a little peek at how it's changing, and Steve's going to be able to tell us about what happened this winter in a little more detail.
Thanks, John. Yeah, so John talked about, what drives these weather systems. I'm going to get into talking about what we've seen as a result of, as John pointed out on the satellite image, the technical term whirlies, and what that impacted the weather and the precipitation in Wisconsin, and how that might then impact the upcoming spring in terms of the measurements and the monitoring that you do. So, John, if you go to the next slide, I think it'll be no surprise to everyone that this winter has been a warm one. And the winter for us is the months of the conditions, the weather conditions, the climate of December, January, and February. And what this map shows is focusing on Wisconsin, but pretty much for most of the upper Midwest, that the normal temperature in comparison this year's temperature in comparison to the normal average temperature that we saw in the past 30 years between 1991 and 2020 was significantly warmer. Southern Wisconsin was 8 to 9 degrees warmer than what we would climatologically expect based on that 30-year period. The upper regions of Wisconsin are 10, 12, 14 degrees above normal. I mean, that's a significant amount of temperature change. In fact, there are a number of times in February when I was reading the paper and getting the average highs and the predicted highs and the predicted minimums. And oftentimes the actual minimums and the predicted minimums were higher than the normal high temperatures for that day. So extremely warm temperatures we've observed. And of course, the other thing that I think we've all observed, particularly if you're monitoring the lakes and the streams, is the amount of precipitation or the lack of the precipitation. And we see that in the next slide. Again, the 23-24 winter, John, if you go to the next slide.
Yeah, sorry.
Was extremely dry. Most of the state, except for the southeast portion right next to Lake Michigan, was 1 to 2 inches below normal in terms of precipitation. And that's if you take the snow and you melt it down. That's how we measure the type of precipitation climatologically and actually. If we're wondering about the snowfall amounts, which is shown in the next slide, John, again, I think it's no surprise to anybody who follows the hydrological cycle of Wisconsin, that again, the normal snowfall for our meteorological winter of 2023 and 2024 was below average. For southern Wisconsin, that was on the order of 10 inches. By the time you get up to northern Wisconsin, that's 2 feet below normal. Again, that's an amazing thing. And as John said, he's a winter guy. He loves winter. This is very depressing. That's why he went to the upper air to try and find cold air, because it's certainly not down here, and neither is the snowfall this year. That's the general picture for the state. The other thing that it got me wondering about is looking at snowfall on the ground, right? Because that's going to be an important aspect as we come to spring, whether it's agricultural, stream monitoring, lake monitoring. And so I picked 2 stations just to take a look at. Eau Claire, you can know where Eau Claire is. That's on the west central Wisconsin, if you will, and then Madison. And the next slide shows you a couple of charts that deal with the amount of snowfall in Madison. And so if you look at the green line, that's kind of flat and then it trends up. That's the accumulated daily normal snowfall. And when we say normal, that for us is average. That's the climatological average between 1991 and 2020. And so you can see, up until November, there really isn't very much. The total snowfall depth, which is on the right-hand side, It's pretty small, but by the time we get into March, the beginning of March, we're talking more than 3 feet of snowfall is what we expect to have had during our winter season. The purple vertical lines, those are the actual snowfall that we observed on that particular day in this winter season. And you can see pretty much there wasn't very many snow events except in the middle of January when we got about 7 or 8 inches of snowfall. The black line is then the accumulated total snowfall depth for the year and is to be compared with the green line. And so if it's flat, then that means, again, we're not have any precipitation during that day. You can see by the end of March, beginning of March, you know, we're about a foot below what we would expect to see in accumulated snowfall this year. What really drove me to look at this figure is how much snow is on the ground, right? What's the depth on any particular day? And that's that light blue line. And the shocking thing to me is, you know, by February, there was no snow on the ground in Madison. Yeah. There was a little blip, you know, in mid-February, we had a little dusting, as I like to call it, but otherwise there's no snow on the ground. And that's going to impact precipitation events that are coming up. At least that's what was on my mind. And again, if we go to Eau Claire, which is in the next slide, John, you basically see the same thing. You know, the amount of snowfall, the accumulated amount of snowfall is way below normal, almost 3 feet below normal for Eau Claire. And again, by February, there's no snow on the ground for February. Now, the other thing that really brought my mind to this is that on Sunday, we had a beautiful day here. It was a beautiful Sunday, and I went outside. My tulips are coming up, so I started out in the garden, and I noticed that the soil was really warm. And then I heard we're going to have thunderstorms on Monday, late afternoon, early evening. And it got me wondering about, well, what's the condition of the ground? How frozen is that ground? Because if the ground was frozen and you get an inch of precipitation, that's just going to run off. But it sure seemed like in my garden, the ground was not frozen. And therefore, precipitation is going to absorb into the ground, and that's going to be good for the garden and not just run off. And so I tried to get, and I go to the next slide, data on the frost depth, because I had heard people say that it was below normal. It's not easy data to find or to digest, and that's because there's a couple of factors that influence the frost depth in a particular region. One is the air temperature, right? We've had a really warm summer. Really warm winter. So to me, I was thinking, okay, that's going to really support a short frost depth in the soil. Of course, the other thing is snow depth. If you don't have any snow in February, that's just going to warm the soil up because the snow will act like if it's there, it'll act like an insulator and keep that ground frozen. And of course, it's the type of soil as well will determine what is the frost depth. So what I did this morning was I actually went and pulled some data. And if you go to the next slide, trying to find out what this frost depth is throughout the state of Wisconsin, because that'll affect agriculture, that'll affect runoff, that'll affect groundwater systems, and particularly with the coming precipitation systems. And this is the map that shows where those observations are and what they were made, what those conditions were early in March, like March 5th, I think most of these were made. You can see in southern Wisconsin, that light yellow green shaded circle means that the frost depth is 0, right? It's not frozen. Is that typical? No. If you look at Watertown, I pulled that year in this year, the frost depth is 0. Last year on March 10th, it was almost 2 feet deep. Similarly, in Plover, it looks like this year it's about 9 inches, which seems like a lot. But when you compare it to last year, the frost depth on March 10th was over 2 feet, 27 inches deep. So the ground is not frozen, which again, depending on what you're looking at for coming precipitation in the spring, that could be good or bad. For me, I kind of like it in terms of my gardening anyway. Of course, when we talk about freezing ground, we could also now talk about freezing lake. And if John, you'll go to the next slide, we'll start looking at ice cover on the lakes. And so This is looking at the Great Lakes average ice cover on a particular day, so running from December out through the end of May. The thin purple lines are for a particular year, and so you can see there's a lot of variability from year to year, but typically what you'll see when you average those all out, you get the red line, and you can see you're about Great Lakes, by the time you get to end of February, March, we're talking about 40% ice coverage across the Great Lakes, climatologically on average. The black line is showing you what the observations were for this winter time. And you can see by mid-February, we're talking about 4% of the lake is covered with ice as opposed to about 40%. So again, we're seeing really low, because of these warm conditions, ice just isn't being on the lakes. And not only do you see it in the Great Lakes, if you go to the next slide, before I go to some local lakes, this is looking at the historical ice coverage of the Great Lakes, the annual maximum ice cover. So one way is what I just showed in terms of the average for a particular day. Another way to look at what is the maximum for a particular season. And again, that last dot is for this meteorological season, and you can see the maximum ice coverage that we had on the Great Lakes was about 20%. Other years, it's more than 90%. The thing about this figure that I like is that it shows, yeah, this is really low, but over the last 50 years, we've had about 8 years in which this type of 20% coverage or less actually occurred. So it's not unknown that we'll have a maximum ice coverage of about 20% or less. In the next slide, we'll look at one of the most studied inland lakes in the world, and that is Lake Mendota. We have a record of the amount of ice when the ice goes on and when it thaws out. That goes back to the mid-1800s. The annual number of days is what I'm showing in this particular figure. The light blue is for every year, every meteorological year. And then just to kind of smooth that out a little bit, we have the darker blue. If you look at that darker blue, you can see that there's a trend in which the number of days in which we'll have ice on Lake Mendota is going down. And in particular, this last decade, it's always been below what the average conditions have been. For Lake Mendota, the disappointing thing, considering I live on Lake Mendota and I like to have ice and I like to go out on the ice within the lake, but I didn't go on the ice at all this year just because I was worried about how thin it might be. But this year we only had ice coverage, only had 44 days. The lake was determined to be frozen over on July 15th, and then it thawed out just a little over a month later on December 28th, so for 44 days. One other thing I want to mention, because again, this gets into the monitoring aspect of how does this winter season impact what we do, well, for fun, I can put it that way. I was, at a curling tournament and talking to a friend who was boiling down his maple syrup. And John, if you can go to the next slide. This was March 1, I was talking with him, and it was kind of surprised to me because I thought you start tapping your maple trees around February. And he had tapped his maple trees. He has, I think he said about 50 or 60 of them in early February. And again, that's that impact of the warm temperatures that we have had. Good conditions for maple syruping, for tapping it as sunny days, where in the nighttime, the minimums are in the 20s and the maximums are in the 40s. And we just didn't have that in February and in March. I mean, we're above the 20-degree minimum temperatures. And so again, that kind of impacted, that kind of weather that we've been having has impacted the maple syruping as well. And then the last slide I want to show, if you jump to that, John, is again, trying to look at what's going to happen in the springtime. What are we seeing? How is this impacting what we might be seeing in terms of lake levels, stream levels, vegetation? And what this map is showing is this year's change in the spring leaf index. So just like monitoring streams, people monitor plants and they look at when do they bud out, when do they flower out. And in this situation, what they're seeing is in January, there was a little bit behind in Texas and in February in terms of when you would expect leaf out. But then you can see by the time it gets up into Missouri, that's 10 days, 10, 20 days earlier than what normally we would predict to see based on the climate of the past 30 years. So that's a brief summary of what causes the weather. And John, if you go to the last slide, and then what we're seeing as the impacts of what the weather was this winter and how it's impacting what we're seeing in terms of ice on the lakes, ground freeze level, precipitation, snowfall, etc. And with that, I think it's time to address some questions that you all might have.
Well, there's one question in the chat so far. Before I get to that, I'm going to give people some time to add more questions to the chat. And last night I was walking the dog, and I thought of a good question to pose to you guys that maybe gets at something that's misunderstood by a lot of people, and that is the difference between sleet and hail. It was sleeting all over us as we were walking the dog, and I thought that'd be a fun topic for you guys to dig into a little bit here.
John, you want to take that one?
Sure.
It's a winter type question, I guess, or no, spring and summer as well.
Yeah, kind of related to both seasons, isn't it? Yeah. Sleet is a refrozen, previously unfrozen raindrop. So, we were in a situation yesterday where we had convective storms and some low-level warm temperatures, and yet some temperatures above the ground that were a little bit colder than that. And I think by the time the night came around, we probably dipped below freezing near the ground and in a layer that was sufficiently deep where raindrops that might have been falling from a level where the air was a little bit warmer than that were falling into a deep enough cold layer that those little raindrops could refreeze, and that forms a sleet particle. They're usually fairly harmless. I think it's their cousin, which is freezing rain, is a lot worse, where a layer of cold air that touches the ground is very much more shallow. And so the drop hits the ground as liquid and then freezes on a cold surface. That's a mess. Hailstones are a result of vigorous upward and downward vertical motions in intense thunderstorms. And that's why Steve had a mention of the summertime in reference to the question. So, and they keep on growing. They just keep being thrown back above the freezing level, accreting more water, and then having it freeze, coming back down below the freezing level in the turbulent vertical updrafts and downdrafts of a thunderstorm. And the number of times they cycle through will determine how big the hailstone gets. And if you really carefully in a laboratory cut a big hailstone in half, you can actually see the different layers, almost like the rings on a tree that indicate how many times it's gone back and forth across that freezing level. That was not what was going on yesterday to form those little sleet particles. So they're quite different in that regard.
Awesome. Thank you for the explanation. So now we have a whole bunch of questions that have been pouring in like sleet. So the first one was a question referring to how warm it's been over the winter time. Do we expect that the summer in Wisconsin is going to be incredibly hot based on what we've seen so far?
So I'll comment, and then John, you can chime in.
Yeah.
I was actually looking at that because the NOAA came out with their predictions for the seasonal forecast and looking at the summertime. And what they're predicting is above average temperatures and below average precipitation, I think is what they were saying. Yeah, for the upper Midwest.
And that combination is it contributes to or encourages a positive feedback. Steve's excellent presentation on the lack of ice in the ground right now means that if it warms up, it's going to take water out of the ground. I think our days over 70 degrees, we've already had 2 of them, have really, dehydrated the non-frozen ground. And that's bad news, not only for agriculture, but it's bad news for the water table, in addition to agricultural interests. If that ground stays dry and it does stay warm, there's going to be a feedback that makes that worse. And I think that might be underlying some of the predictions that are being made for the 3-month tendency. I guess I'd only throw in a little word of caution. If we get a soaking rain or a soaking second half of March, that part of the problem at least is alleviated. Yeah. So it could change almost on a dime. But those kinds of background conditions are really the things that can, even at this long range, kind of get you nervous that, hey, maybe we are setting ourselves up for something unusually warm. Though I think the last comment I'll make is that there's no real systematic connection between the wintertime anomaly and the spring and summertime anomalies in terms of temperature. It doesn't last that long. The memory of the atmosphere is very short. So unless there's one of those feedback mechanisms at play, it's probably not something that can be easily and confidently predicted.
Okay. There's another question regarding the frost depth. Maybe we can just take that one right now and expand on it a little bit. How would that low frost depth or zero frost depth affect stream and lake levels in the springtime?
Yeah, that's a really good question. And there may be experts on this call who could probably answer it better than me. But two things come to my mind what really kind of drove me to look at that. I really wanted to find ground moisture data, and it was easier to find the freeze depth than it was for me to pull up the ground moisture data. How it would affect stream runoff is that if the ground were frozen, any precipitation like southern Wisconsin had yesterday, a lot of that would just run right off and down into the rivers for those who live by rivers. The other part of that is the soil moisture part of that, where if the ground is really moist, then that's going to push downstream. The water pressure in the soil is going to be flowing down to the streams. I know we saw that in, I think it was 2004, where we had a lot of flooding down here in southern Wisconsin, and the ground was soaked to the point where we're on well water where we are, and our well cap turned into an artesian well. There was so much water pressure in the ground that it just pushed the water up out the well cap. And so how much water obviously in the soil is going to help support how much water is going to be in the stream flow. And I'm not sure. I would imagine that the ground right now is pretty dry, just because we haven't had any precipitation, and much of the region is really, the frost line is much shallower than what it typically would be at this point.
Yeah.
Okay, thank you. Next question is there a history of weather turning colder, and what would cause that?
You mean at this time in the year, probably?
Yeah.
Maybe or historical cooling trends at times?
Yeah, historical cooling trends. Well, volcanic activity can be a factor if it comes at the right time of the year or in the right time in a seasonal cycle. It can turn a season really cold. That's happened a number of times. We had, in fact, the temperature record over the globe, the average temperature record reflects that. Even in the last 150 years, the instrumented record, there was a period of volcanism that was fairly active in the 1940s, I think, and there's an obvious decline in the global average temperature in the 1940s responding to that. Pinatubo in 91 brought the global average temperature down. So things like that, they're almost these gigantic effects. There's a very, very long-term variability on the Earth's orbit around the sun and its obliquity, its tilt of its axis. So that has a role to play. But, most of those long-term trends are being dwarfed by the short-term trend of industrialization, which is changing the composition of the atmosphere. So it's volcanoes could challenge the industrialization because they do almost the same thing but opposite. And but until and unless we have a big period of volcanism, again, we're not going to probably see a turn to systematically colder. No.
Okay. Next question is if the Gulf Stream begins to shut down, the Northeast will likely get colder, and what impact might be seen here in Wisconsin?
That's a good question.
I'll let you take that, John, because didn't we just talk about that?
Yeah, a little bit. I'm talking about the alleviation of the surplus deficit that I brought up in the first part of the presentation. 30% of that is done by ocean currents, and the Gulf Stream is one of two really warm ocean currents in the Northern Hemisphere. So, if it were the one that would kind of suddenly decay to nothing, you're going to have some substantial fraction of 1/3 almost of the surplus deficit no longer actively being satisfied. It is really hard to understand or to know what would be the ramifications throughout the whole ocean atmosphere system upon an abrupt cessation of the Gulf Stream, because I think there'd still be this requirement to balance the energy surplus deficit. and it would have to be taken up by something else. And my guess is one possibility would be more intense mid-latitude storms, but I'm not sure that that's the leading possibility. And I don't know if other ocean currents would pick up the slack, but it's a dangerous prospect to have to consider. I don't know if I've heard anybody's prediction on what would be the ramifications in terms of other agencies getting involved in a way that they're not currently doing. I don't know.
Okay, the next question is, why does Florida have these late afternoon downpours and Wisconsin tends to have these all-day gentle soaker storms?
That's a good question. You want to go, Steve?
Yeah, I would say in the summertime, we get that kind of storms as well because they're driven by convection. And a lot of what Florida gets is convective type precipitation. Whereas in the spring, fall, winter, it's more common for us to get precipitation associated with these fronts that John was showing earlier in his talk. And those are typically more steady type precipitations for coming rather than from convective clouds, stratiform type clouds.
So in other words, the ground is heating up during the first part of the day in Florida, and those convection currents are creating their own little storms in the afternoon.
Yeah, and it has to do with the stability of the atmosphere as well. So as the ground gets heated up and the upper atmosphere over Florida is relatively cool in comparison to the lower atmosphere, once that air begins to lift, it can just take off by itself. And that'll lead, if there's dynamical support, upward motions and not sinking motions, as John was talking about earlier, then you can get those rapid convective clouds. But again, we get them here in Wisconsin,
Yeah,
particularly
right.
in the spring and the summer.
The next question gets at the drought question. I think we've pretty much covered this one as well as far as predicting a drought year. It is possible to predict low precipitation upcoming, right? And 2024, I believe we said it was predicted to be warmer with less precipitation, right?
Yeah, and I'm going to change the wording on that because we typically talk about the predicting, yep, it's going to be a dry year. When they do those forecasting for seasonal conditions, whether it's precipitation or temperature, the National Climate Environmental Institute or whatever it's called, and part of NOAA that does that, really talks about the probabilities of it being drier than normal or warmer than normal. They really don't get into it's going to be 1 degree warmer come the summertime. They'll come in and say there's a good probability, 66% or 90% chance that it will be warmer than what we've observed during the previous 30 years.
Yeah, that's a good comment.
Okay. Next question gets to the ice ages in the history of the Earth with warming periods in between. Is it known if what we are experiencing now is similar to the past in between ice age periods?
Right now, we are changing the chemical composition of the atmosphere. We have been for the last 100 and some odd years in a way that has no precedent, at least in the last million or so years. So we have a carbon dioxide fraction last month, February, or maybe January is the last one I think I can quote, was averaging 422.96 molecules per million in the atmosphere. And the long-term historical record that we can get from Antarctic ice bubbles, from ice cores, bubbles from the ice cores, the peak has been somewhere between 280 and 300 parts per million, all the way back 800,000 years. And so we're in completely virgin territory. And so if there is a background long-term, and the long-term cycles that are natural variability are 50 to 150,000 year cycles, we're dwarfing that right now. So everything we're talking about in terms of global warming is in addition to, or completely overwhelming, if it's in the opposite sense, any trend that's part of the natural variability. So it doesn't do us any good to be concerned about what the background natural variability is. And in fact, I think we're in an interglacial warm period. Is that right, Steve? I can't remember all that stuff.
Yeah, I think we're right. Yeah.
Okay. How does this winter compare with other El Nino winters?
Well, this winter is by any measure either the first, second, or third warmest. Steve showed some regional evidence for that. I have some hemispheric evidence for that. And there have been other years in both of the time series to which our comments referred, where there have been strong El Ninos. 82, 83 is one. There's been some other ones. 71, 72 was a strong one. So at least in the cold pool analysis that I've done, I was asked by reviewers, blind reviewers, to say, hey, don't make these conclusions until you'll check whether it's related to El Nino. And so I did that analysis in response to that request. And it turns out there's no particular relationship between El Nino historically and how cold it is over the whole hemisphere. However, I'm open to the fact that this particular year may be a conjunction of a lot of circumstances that may give it a little bit more play. But I think just looking at other historically strong El Ninos, we didn't have this kind of a warm winter, either globally or hemispherically or over North America. So it doesn't seem like it's a leading factor.
Okay, speaking of global weather, is this weather change that we've been seeing this winter occurring all over the world, or is it somewhat isolated around here?
There's no snow in the Alps right now. I have a friend, colleague. I have a colleague in Switzerland who was planning to take what their equivalent of spring break is to go skiing early March. No snow. They had to turn it into a hiking expedition instead. So it was a very early spring in the Alps, as one anecdote. And my measure is hemispheric. So the hemisphere suffered from being abnormally warm. That doesn't mean every location does. And I understand that's the part of your question. But at least that's one anecdote that says it's kind of widespread.
Steve, did you have a comment on that also?
No, I was going to say, and John ended up by saying, and that is that there may be regional areas where you may see much differences than over large areas, just like you would probably find in the U.S. as well.
Okay. The next question is, are we seeing similar below normal trends in annual rainfall as you've described in annual snowfall?
I'm not sure. I'm not sure, John. Do you know? I haven't really looked at annual rainfall.
Yeah, annual rainfall, I'm not as confident about, but there was some months ago, I think in anticipation of the winter, we did one of our columns on snowfall. And
Right.
the annual snowfall is highly variable, and there's in Madison anyway, and there's no systematic trend in it, from what I could tell. I made a graph of it, kind of put it through some statistical analyses. There doesn't seem to be any systematic trend, but it's so extraordinarily variable from year to year. That might be why there's absolutely no way you can detect a trend. So as far as I know, the snowfall, at least in Madison, does not exhibit evidence of any systematic decrease.
And we wouldn't, I mean, similarly, we could say the same type of condition. I'm not going to predict whether there's a trend or not with regard to precipitation, right? Because it's also really variable in terms of if it's going to be steady or heavy or what.
Yeah, I think that kind of comment is in the realm still, or that prediction is still in the realm of prediction. It's not really established fact that we're already drying out in a systematic way. I think you're right about that.
Yeah.
The next question gets to the lag in warming in water compared to the air temperatures in the spring. So we see lakes warm up much more slowly than we see the air temperatures warm in the spring. And the person's wondering, is there a known average lag time of this change in warming of the water compared to the air temperatures?
I mean, that's a good question. The first thing that comes to my mind would be, well, two things. One is, yep, when it's a clear sky, that sun is going to warm up the water if it doesn't have a layer of ice on it, for sure, or snow on it. The other question then would hit my mind is we'd have to separate that out from cloud cover as well, because cloud cover will tend to ameliorate that effect, that impact. So I'm sure there is. I don't know exactly what that lag would be, and it would be a function of one, is it clear? Two, is it cloudy? And what type of cloud? Is it a low stratus cloud or a high cirrus cloud?
Yeah, those are all good comments. There's a seasonal temperature lag between when the summer insolation is maximum in late June and the actual high temperature for the year is found. And that has to do with the water. So maybe that's a way to broker the difference here. It takes about, I think 70% of states in the union have their maximum summertime temperature all time more than 3 weeks after the solstice. So there's at least a 3-week lag. And I bet your lakes are probably in the same realm. They're probably not that far off, depending on their depth.
Yeah, that might be the way to get at the answer to that question, is to look at those and how that lags on average.
Yeah.
Yeah, I think I would also add that the depth of the lake or the total water volume
True.
and the color of the lake sediments can have a big impact on that as well. And shallow bays with black sediments that are only a foot deep will warm up pretty quickly.
Yeah, that's true.
The next question is, how does wind speed change with these warming weather patterns? Are winds becoming stronger?
I'm not sure if the surface winds, we've gotten this question a number of times, haven't we, Steve, over the years? And I never seem confident in my answer. I can say something about the jet stream winds. They're not getting any stronger, and that's recent result of research. So that's kind of in contradiction to some climate predictions that they're getting wavier, but not stronger in speed. But what do you think about the surface wind, Steve? I think you've looked at that before.
Yeah, again, we've looked at that before. And again, it requires more detailed analysis than looking at average wind vanes, and then they're called wind vanes, where you look at the maximum wind coming from a particular direction. Because
yeah, I know what you mean.
Yeah,
wind
what do you call those? Windrows, right?
Windrows,
yeah. Because I think sometimes it feels like it's really, really getting windy, but it may be associated not with the wind speed, but the wind speed at my particular house because of the direction that the wind is coming from, which would be right off the lake in some situations, and that's when it really seems windy. And from the backside, then it doesn't seem as windy.
Yeah.
But I think I'm pretty sure that I looked at maximum or average wind speeds with time in the Madison area, and there was no real discernible trend.
Right.
And then that what got me looking at, well, what's the windrows say? Well, as a function of a particular direction. I guess we'll have to look at that more carefully, since we got this question now at least twice in the last 2 weeks.
Yeah, it comes up a lot. It's an interesting question. We had a windy day on Sunday, so it's probably in people's minds. It was really windy Sunday.
Yeah.
So it is just about 1 o'clock, but you guys did say that you could stick around for a few extra minutes to take the remaining questions. Is that still okay?
Sure.
Yeah. Okay. So the next question is,
we don't guarantee we'll be able to answer them, though.
And we'll always make one up, though.
Right.
The next question is about the pressure change needed to drive a seiche. And this may vary between the size of water bodies, but maybe you could touch on what a seiche is, and then if you have an answer to that question.
So a seiche is driven by a rapid change in atmospheric pressure, if I have that correctly. And so I think we see them with big wind events and maybe convective storms. Does that sound right, John?
Yeah, I think so. I think you've told me more about them than I've told you about them over the years. I think I'll agree with anything you say because I think you know about it. Yeah.
Yeah.
I think that's right.
And so I've never experienced one, but I've heard of people who have, and that just sloshes back and forth between. Oh, maybe I got it wrong. So if the wind's coming from a particular direction, it's pushing the wave. So you lake folks can correct me if I got this wrong. So the wind's coming from particular directions. It'll pile up the water in one way, and then when the water weakens, when the wind weakens, then that water swishes back, and that's what a seiche is. Is that right?
Right. It's more common on large water bodies.
Large bodies than in small ones. Yeah.
Okay, so in that case, it might not just be a pressure change, but this propagation speed of the weather system that had the low pressure in the first place, that when it's moving away from you really quickly, and the next incoming system where the pressure is higher and kind of a flatter gradient comes in equally rapidly, that might be the thing, the propagation speed of the system. rather like storm surges for hurricanes. How fast they move is really a big factor in how much of how deadly the surge is, how fast it gets on shore.
The next question is, does debris in the atmosphere that results from the wars on the other side of the Earth impact our day-to-day weather here?
Probably not. And the reason why I say that is when John was talking about like the volcanoes and how they can disrupt global temperatures, those volcanoes, they have to throw their ash and their materials or gases up into the stratosphere where they can stay for a significant amount of time. In the wars that from the photos that I've seen are generally low in the atmosphere, and so that debris will either be washed out by weather systems or gravitationally settling before it could actually get widespread around the globe.
Yeah, and I remember one example. Steve, you were involved in this project, weren't you? I know my PhD advisor was. After the Iraq War, there was all those oil fields were ablaze.
That's right.
And there was concern that it was going to be a global, climate perturbation, and it wasn't even a regional perturbation. All that black smoke. I remember that was a really seemingly contradictory result, but everybody seemed to verify it, no matter how you looked at it.
Yeah, actually, I forgot about doing that study. Yeah, that was interesting.
The next question is the snow belt moving south in the state? This person is from Oconto County and noticed that lately it seems that there's more snow in the southern part of the state than there is in Oconto County.
This would be a bad year to make the guess. On that. Superior and places up there were like 3 or 4 feet below their normal, or even more than that. It was just outrageous. So I don't know that that's true. I don't think there's been any systematic change in the storm track or the inland penetration of cold air outbreaks that can spawn lake effect snow, if that was one of the mechanisms that might account for that. And if that were happening and you're getting snow in Oconto County, but you're not getting it near Superior or something, that would be a weird circumstance. So I guess I'd guess no, but I don't know the answer.
Okay. That is the end of the questions in the chat, but I have one thing I wanted you guys to comment on. So about 20 years ago, I took courses in meteorology and forecasting, and a lot of people like to pick on the weather guy for being wrong. And so I thought maybe you could touch on just how difficult it is to predict the future.
I'll make a couple of comments and then turn it over to you, John. But two things. Two things come to my mind. Our forecasting for 2, 3, 4 days out is really accurate, to the point where you see a lot of people they want to know what the temperature is going to be. They pull out their phone and look it up, and they have confidence that it's going to be warm. The other thing I'll point out is the groundhog is only correct 40% of the time. So we're way better than
Right.
the groundhogs.
And 40% of the time is less than a guess. I mean,
Right.
you have to try hard to fail by that 10%. It's amazing. A revolution, though, in weather forecasting has taken place in our lifetimes. If you're over 50, certainly it's taken place in your lifetime. If you're in your 20s, it's taken place to a degree, even in that short of a lifetime. Steve is exactly right. In the old days, and we'll talk 25 years ago, you would never get even a mention of a forecast beyond 3 days in any broadcast media. They wouldn't even bother doing it because there was no particular sense of confidence about it. Now you routinely say forecasts out to 7 or 8 days. And though that might challenge, the threshold at which you can have great confidence, it does testify to the fact that what used to be short range, 1 or 2 days, now encompasses all the way to 4 days. Medium range is 5 to 8. And we're making reasonably accurate medium range forecasts every single day. And this behavior that Steve points out about people resorting to their phone would absolutely not occur in the absence of systematic accuracy. And so we've made great strides with our observing network. Steve's been a leader in that with remote sensing of the atmosphere, and that accounts for about 30 or 40% of the observations that go into the numerical forecast models, maybe more. I'm probably behind the times. The understanding of atmospheric processes, the ability of computers to take charge of the billions of calculations required. That keeps on getting better and better. So everything's pointing in the direction of improvement, and we've made good on that. So it's really been an exciting period of time in our science, if one is interested in prediction of weather systems. I think people may be making the mistake of translating or, sort of projecting that same kind of skill and excitement about it on climate forecasts. And they're totally different forecasts. And so that's a danger, but we have to do better public relations to get that point across.
I think one of the common issues is with a percentage chance of precipitation. So if there's a 20% chance of isolated thunderstorms, is that a probability of 20%, or is it that 20% of the area will likely see, the forecast area will likely see that precipitation event?
I interpret it, and I think this is correct, but I could be wrong, but it's certainly not wrong in my interpretation. I interpret it this way, that a 20% means there's a 1 in 5 chance you're going to have a thunderstorm because the conditions are of that kind. They're not over the top certain, but they're not, over the top on the other way, saying there's just no chance. I don't think it's point specific, because the areas that the Weather Service is making forecasts for are pretty regional already anyway. They may, in fact, in Milwaukee County or Sheboygan, they'll actually say things like, lake afternoon showers or on the lake breeze are likely. And that kind of eliminates the guesswork in that instance about what 40% means, because they're telling you if you're in the lakefront region, you have a better chance.
All right, I think we've exhausted all of our questions. They had a couple minutes to put more in the chat. I don't see any more coming in, so we'll call it a day here. I'm really glad you guys could join us for the last of the water talks this year. It was great to have you guys. Thanks everybody for joining. We still got about 50 hanging in here with the question and answer session. We got up to 82 at one point. And our next winter water talk series will begin in November of this year. So we look forward to seeing you all then.
And I'll add a thank you to all of you for doing the voluntary work you do in making these observations, because they're really important for people to make them and to make them available. So thanks to you too.
Yeah, I agree. And thank you for having us too. This was really fun.
It's always fun to talk weather, right?
Yes.
It's never boring, Paul. Never.
Yeah.
And we're mostly right too.
Yeah. Right.